Thank you very much for the introduction there. What I'm going to do today is to give two lectures, and normally when I give a lecture the chairman shuts me up at a certain point, but now I could do two. I could tell you everything more than you really want to know about the climate change and the Arctic and what it's doing to us. So in this first one I'll be talking about the actual the behavior of ice on the planet, what it's doing, why is it disappearing, and what are the implications of that. We know that the sea ice in the Arctic is vanishing, and finally that's being accepted that it's happening because it is happening. But the general view is, well, so what? There's a lot of change going on in the world. Things that we're used to are disappearing. The glaciers on the top of Kilimanjaro are melting. It doesn't matter to the rest of the world if sea ice disappears. But in fact, it turns out that it does. It turns out, in fact, that the consequences of sea ice disappearance are more severe than the actual fact of sea ice disappearance itself, because there are feedbacks which have impact on the entire global atmosphere, in the entire global climate, and those impacts are much more serious than people have appreciated. So I'm going to start by talking about the ice itself and how it behaves. Then I'll start talking about the impacts, and I'll deal with a couple of them in this lecture. That's the way in which global warming is accelerated by the loss of ice, which changes the amount of radiation reflected back into space, so the albedo of the planet. And then I'll talk about how the disappearance of ice accelerates global sea level rise. So then this afternoon I'll talk about the other impacts, especially the ones which this conference is very concerned with, which is the impact on food production and the impact on weather and what that means for the people of the planet, and therefore what we ought to be doing about it, and ending up with a plea for taking carbon out of the atmosphere as the way to save ourselves. So I'll start off by talking about the ice itself, and this is already I've done it wrong. Right. Well, there we are. In talking about the loss of ice, I'm obviously also promoting my book on the subject, which came out in England at the end of 2016. The title was stolen from Hemingway, and it came out in the US updated because things have gone on have advanced very much in a year. All the ice concentrations in the Arctic have gone down, so it's got new graphs in it, and came out in September with the Oxford University Press in the US. And it's also, in case you travel globally and speak other languages, you could find an Italian edition, a Dutch edition, a Japanese, Chinese editions. And the latest one is the Italian edition, in fact. But the most attractive one is the Dutch edition, because that's got more pictures in. But unfortunately, I can't read it, and nor can anybody else that I know. Anyway, we start off by, let's look at what's happened to the Arctic Ocean. For people who go there frequently, the changes are actually enormous. So this is the Arctic as it was in 1970. This was the first time I went to the Arctic and was sailing through the Northwest Passage on a Canadian oceanographic ship. And there's the ship up there. Oh, there it is, called the Hudson. It was accomplishing the first circumnavigation of North and South America on a voyage called the Hudson 70 expedition. That was the first, in fact, the only time that a ship has sailed around North and South America. So I was very lucky as a young graduate, I was able to be a low-grade research assistant on this ship and actually sat on board for the whole voyage. So I was accomplished the first circumnavigation of the Americas on this ship. We sailed from Nova Scotia down through round South America to the Antarctic, up through the Pacific, and then the last leg was coming through the Northwest Passage from Alaska, through the Canadian Arctic, back to Nova Scotia. And as we came across the north of Alaska and sort of turned right at the Bering Strait, this was the ice we ran into. It was summer, and the ice is broken up, partly melted, but you could see that it's still a very, very formidable barrier. This ice is called MultiYear Ice. It's more than a year old, some of it's several years old. It's very thick, 3 or 4 meters thick. The ship could push through it. It wouldn't have been able to break it. But these are very formidable ice flows, rugged, very, very thick. And this is just a few miles off the coast of Alaska. So there's this, then there's about a mile or two of open water, then you have the north coast of Alaska. So this is what you found in that area in 1970, and then in contrast, we look at 2014, which was a more recent voyage I was on up there. This is the Healy, US Coast Guard icebreaker, and we're now in the same longitude. We're off the north coast of Alaska, but we're 300 miles north of the coast. So instead of being 1 or 2 miles of open water, there's 300 miles of open water, and the ice is very pathetic, as you can see. We weren't even allowed to stand on it by the captain in case we fell through. So it's very thin, it's rotten, it's melting, and in fact, within a week or two of that voyage, we were sailing further north, and the ice was melting as we went. So that's both at sea, the southern part of the Arctic Ocean today, which as you can see is completely different from the way it was in 1970. Well, let's look at something's happened, obviously, to the ice in the Arctic. It's disappearing. But let's look at ice in the world and what's been happening to that. So if we do that. The challenge is to make this thing go backwards. The bottom one. Okay. I'm free to walk. This graph is on several different scales. It takes us through history. It's quite nice because you change scale. So from 100 million to 500 million years ago, the average temperature of the planet, which is the vertical scale, it oscillated about a lot. We don't understand why, because it was such a long time ago. The distribution of continents was different. But on the whole, it was several degrees warmer than it is today. The zero is the present average temperature. And so we're looking at 15 to 20 degrees warmer than it is today. Then when we came through a period called the Eemian, which was about 40 or 50 million years ago, the planet started to cool off, and it gradually cooled off through that period from 60 to 10 million, and then it cooled off some more between 10 million and 1 million years ago, and we got into a state where the planet was just about cool enough for ice and snow to form, and but it didn't happen that we had sort of moving into an ice-ridden planet. We had an oscillation between an icy period and a non-icy period, and those are the ice ages between deep ice age and interglacial, and that's actually driven, that's these little oscillations here over the last few 100,000 years. Those are driven by astronomical factors, in fact. There's it's called the Milankovitch variations, and they named this after Milankovitch, who was a Serbian geophysicist, but really and truly the person who discovered these oscillations was called Kroll, and he was an uneducated Scottish wonderful person. He worked in a research institute in Edinburgh as a janitor, and he read all the books in the library, and he kept coming up with brilliant ideas. So he was an unschooled genius, and he never got, of course, any credit, but he does now, because the Scots are very, very proud of him. So they should be called Kroll variations, but they're actually called Milankovitch variations. And what happens is there isn't any change in the total amount of radiation reaching the Earth from the Sun, but there's a change in the seasonality of it, and that's enough to produce a change in the total amount of heating of the planet. This is because as the Earth is tilted on its axis at an average of about 23.5 degrees at the moment to the plane of its orbit around the Sun. So it's tilted, and that tilt is the latitude of the tropics, and 90 degrees minus the latitude of the Arctic Circle. So that tilt changes with time. Gradually, over a period of about 100,000 years, the tilt of the Earth's axis relative to the plane of the Earth's orbit goes through a sequence that takes it from about 21 degrees to about 25 degrees. So the Earth is gradually, it's like a top which hasn't been quite wound up enough, and it's wobbling. So this is called the Chandler wobble, and it does make a difference, and it means that the latitude of the tropics, of the Tropic of Cancer and Capricorn, and the latitude of the Arctic Circle changes with time, and over a distance of about 200 or 300 miles. That's enough to change the distribution of radiation reaching the Earth. And when the Earth is tilting a lot, then there's more radiation reaching the northern hemisphere relative to the southern hemisphere. And the southern hemisphere is mainly water, the northern hemisphere is mainly land. And that affects the absorption of that radiation. So the story by Milankovitch is that although as a ball sitting in space, we get the same amount of radiation from the sun, whatever happens, in practice, that radiation is not distributed uniformly between northern and southern hemisphere because of this Chandler wobble. There's also a couple of other wobbles. One of them is that the Earth's orbit, which is an ellipse, it flattens out and then becomes more stretched, again over about 100,000 year period. That's the second variation. And then the third one is that the whole orbit precesses, so that the time of year at which we're closest to the sun changes with time. And at the moment, the northern hemisphere is closest to the sun in February. That's now, so you don't feel it, but we're closest for the entire year. We're now closest to the sun, and that changes again with time. So there's these three slow variations, and when you add them together, they give you a variation in radiation received by the Earth. And that's enough, according to Milankovitch anyway, to make a difference because the Earth is just pitched on this boundary between having ice and not having ice, then the Milankovitch variations cause the Earth to go through a cycle of being very icy with glaciers everywhere. That's the Ice Age, and then coming out of that and going into a warm period called an Interglacial, which we're in at the moment. So it couldn't start doing that until it had cooled down. So it didn't start doing that till about 1 million years ago. And then it's been doing it ever since, with periods of about 100,000 years. And now this last bit of the map shows us that's expanded. That's what's happened since the last ice age ended, which was 20,000 years ago. The Earth came out of the last ice age and came up to this present state, which it's been in for about the last 10,000 years. That's an interglacial. We've been in it longer than most interglacials. In fact, we're set. We ought to be set to start descending towards another ice age, but it looks as if, thanks to man's activities, we're not going to do so, and we're going to miss out on the next ice age. That's whether that's good or bad. I don't know. It depends how you feel your great-great-great-grandchildren would feel about that. So that's the situation. These Milankovitch variations causing ice ages, but only for about 1 million years, and then before that the Earth was warm all the time, everywhere. Now, if I can get this to go. Okay. No. Yes. Oh, yes. Okay. So when we can work out in very great detail what happened during the last 4 ice ages because of drilling cores through Greenland and Antarctica, because Greenland ice sheet and Antarctic ice sheet gradually build themselves up with layers, annual layers of snow that get compressed into ice. So if you drill right down through the ice sheet, which is a couple of miles thick, you'll go through these layers and you'll go back in history. So it's telling you that the climatic history of the planet is coming out of this ice core record. And ice cores have been drilled through the middle of the Greenland ice sheet and the Antarctic ice sheet, and they both show the same sequence of events. And we know what the temperature was in these ice samples because of there's 2 isotopes of oxygen, oxygen 18, oxygen 16, and when snow falls, the ratio of these 2 isotopes depends on the temperature of the snow. So this is really like a temperature gauge, which tells us the temperature of the planet back through 500,000 years. And the other thing is, which is just when scientists started to drill, they were able to get this temperature record out from the isotopes, but then they got more clever and found that there were tiny little air bubbles in the ice that have, as the snow fell and compressed, little air bubbles were left and got even more compressed. And the air bubbles, if you extract the air very carefully with a tiny syringe, you can measure the carbon dioxide content. So we know what the carbon dioxide content of the atmosphere was back 500,000 years, which is, I think that's an amazing discovery, because we can tell what the natural carbon dioxide content of the atmosphere is. And so here we have the top one shows the actual record of temperature. So it even though the Milankovitch variations are a smooth curve, the actual response of the Earth is a sawtooth pattern, and that's because it's easier for glaciers to melt than to form, because a glacier forms by snow falling each winter on some mountain, and it doesn't melt in the summer because the climate's got colder, so it gradually builds up in thickness. So the amount of ice in glaciers slowly builds up, but it can only build up at 1 layer a year. But then if the climate gets warmer, the whole glacier can melt very quickly. So it's possible for the planet to warm up more quickly than it cools down. So here we have these sawtooths where we come quickly out of an ice age. That thing on the left is how we came out of the last one. but we sink slowly towards an ice age. That was the period of the last 150,000 years. Then we came quickly out of that one, and there's the previous ice age, which we sank slowly towards, came quickly out of it, and so on. So we managed the record shows 4 ice ages, but then you get down to the bottom of the ice sheet and you run out of ice. So you can't really go further back than that, but that's quite a long way. And the carbon dioxide record is exactly the same. So first thing we know is that high levels of carbon dioxide in the atmosphere are associated with warmth. We know that today because we're doing the experiment of putting more in and observing that the planet gets warmer. But in the past, there was a natural correlation that when there was a lot of carbon dioxide in the atmosphere, the planet was very cold. And we noticed that the variations between the warm period and the cold period are very similar in the levels of carbon dioxide. That when we're in the middle of an ice age, there's a low level of carbon dioxide in the atmosphere, about 180 parts per million. And then when we come out of that ice age into a warm period, we get up to about 270, 280 parts per million. And it's amazing how similar those two levels are between the interglacial and the glacial. What it means is that the Earth has a natural cycle here, that it goes driven by these astronomical variations, but we go from warm slowly down into cold with with glaciers forming everywhere. The carbon dioxide content slips from 280 to 180, and then we come quickly out of that, and the carbon dioxide content goes right back to where it was before, to 280. Then we sink slowly down again. So when the Earth is in its warm period with minimum ice, the natural level of carbon dioxide in the atmosphere is 280 parts per million. That's the balance between plant life, animal life, the processes that generate carbon dioxide, the processes that use it, respiration, or producing it, and transpiration, using it. Then when there's less vegetation on the planet and with more ice, the natural level is 180. Then the bottom picture is also, you can extract dust out of these little bubbles, and this just tells you how dry the planet was. And it's not such a good correlation. It tends to show there were a lot of periods when the Earth was very dry with a lot of dust in the atmosphere. But the top two are the main ones, and it was very exciting to see this carbon dioxide curve come out and match the temperature curve for the planet. So that's what we know about the last 500,000 years. Here we are. Oh, no. Anyway, we had this natural tendency to, when we came out of a glacial period, to go up to 280 parts per million of CO2. And this shows the last 10,000 years since we came out of the last ice age. And we can see that up here, the Earth went up to 280, and amazingly, it stayed at 280 from 10,000 years ago right to the middle of the 19th century, right to sort of 150 years ago. So the Earth's natural balance, its tendency to want to have a CO2 content of 280, if there's no humans around to screw it up, was maintained right from the end of the Ice Age, from 10,000 BC right up to 1850 AD, and then we started to burn coal, and Trump would approve of that, but we started to burn coal with the Industrial Revolution, and we were, for the first time, we were changing the atmosphere of the planet ourselves by burning coal and having the steam age. And we can see that that had an immediate impact on CO2 levels. So we were up at this sort of 280 level, which was natural, and then about 1850 we started to burn coal, and everything was coal-fired in the early Industrial Revolution. Of course, then we started to burn oil as well, but coal was the starter. And immediately the carbon dioxide concentration shot up. And we know that now from things like records of tree rings and thermometer records. In the 1850, there were the beginnings of meteorological institutes, and people were measuring temperatures with thermometers. And so that CO2 content went right suddenly up. And following it was the methane content of the atmosphere, which also had reached some level, natural level, and then shot up as soon as we started the Industrial Revolution. And the bottom one there is nitrous oxide. But the most important gases that have a greenhouse effect are carbon dioxide and methane. So that shooting up, initially, firstly, people didn't know it was happening because amazingly, we weren't systematically measuring carbon dioxide in the atmosphere until 1958. Nobody thought to bother to do it. And then there was an observatory built on Mauna Loa by Scripps Institute of Oceanography, and they've been measuring CO2 there and then lots of other places ever since. But until 1958, nobody was measuring it. But it had been predicted in 1896 that the CO2 levels should be rising and that this would have a global effect. And so this was a really far-sighted prediction. But the prediction, the person who predicted it said, well, we don't have to worry about that because it will all be absorbed by the oceans. And everybody said, oh, fine, okay, nobody bothered to measure it. So for about 50 years after we started to mess up the atmosphere, we didn't know that, firstly, we didn't know that we were doing it, and secondly, we didn't have any basis to calculate why we were doing it. Then in 1896, there was the first paper on what was going on, that we were changing the radiation balance of the planet, but he didn't seem to really think it was too serious. Now we know it is serious and we're measuring it. So it took a long time. So there was some excuse for us doing nothing about global warming for the first 100 years, which was either that we didn't understand the theory by which global warming affects the planet for 50 years, and then for another 50 years we understood the theory, but we didn't have any measurements because nobody was bothering to measure CO2 levels. Now we haven't got any excuse, but since 1958, but we're still not doing anything very much. Okay, let's. Okay, well, this warming of the planet obviously is going to affect a lot of different aspects of the planet, and so the first one that I'm going to talk about is sea ice, and it was very difficult to measure ice extent in the Arctic because until about 1960, because there were only a very few explorers would go into the ice, and there were a few in Scandinavian sealers and whalers would work around the edge of the ice and send back reports on where the ice edge was. So there was, with enormous difficulty, it was possible to get some idea of ice extent in the Arctic. And then after about 1950, there started to be regular airborne patrols mapping the ice limits. The Air Force, navies, the US Navy, and then a lot of meteorological institutes in Canada and Europe were flying aircraft. And then after 1970, satellites took over, and now it's very easy because you just look at a satellite picture, you can see exactly where the ice is because it's white, and you can measure it. So we have very exact pictures now of how much ice there is in the Arctic. But peculiarly, the retreat of ice in the Arctic in summer seems to date from about 1950. So I'm a bit suspicious of that because I think all the measurements done before 1950 are suspect. But once we started to be able to do measurements, we saw the ice going down in area. So the brown curve here is the ice in summer, during the summer months, and that's was decreasing fastest. The other curves show the ice during other seasons of the year. And it seems that in other seasons the ice wasn't decreasing so much, but that's because in the winter the whole of the Arctic Ocean is frozen right to the coastline of North America and Asia, and some more besides in Bering Sea and Greenland Sea. So if the climate improved, or got warmer rather, there wasn't scope for the ice really to retreat. It still wanted to be right up against the coast. So in winter, you didn't see a decrease in ice area, but you did in summer because the ice moved back a little way from the coast. So we have this brown curve, which is the summer ice extent, becoming noticeably decreasing from about 1950 onwards. And okay, I keep pressing the wrong button here. Okay, so it wasn't all that noticeable at first, but then gradually, as I said yesterday, with exponentials, you don't notice anything is happening, then everything seems to happen suddenly. And that happened with the ice extent. And in 2005, it was the first year, which is not long ago, the first year in which the ice really moved back a long way from the coastline in the summer. So instead of having an Arctic Ocean that connected up Europe and North America and Asia with one great solid slab of ice, we have an Arctic Ocean which is a real ocean in summer. And so the pink line here is the average over the previous 30 years of where the ice edge lay in September. That's the month of greatest retreat. And so that's still lying close to the coastline. Then in 2005, it had retreated far enough that you've got a very big slot right across the north of Russia and across the north of Alaska and through the Canadian Arctic. So it was possible for a ship to sail across the Northeast Passage, the Northern Sea route, north of Russia, and get from Siberia across to Europe without hitting any ice. And to a lesser extent, you could do the same with the Northwest Passage. So 2005, suddenly the world discovered two new sea routes that weren't there before, the Northern Sea route, north of Russia, and the Northwest Passage, as being routes that you could send ships through, send merchant ships. So that was 2005, the first year in which the Arctic sea ice really shrank to a level where you thought of it as a floating mass of ice instead of a solid mass of ice connecting the two continents. Then 2007, a huge bite got taken out of it, and it retreated even more. So the Beaufort Sea, which is the area north of Alaska, between Alaska and North Pole, suddenly became a blue sea. And as somebody said yesterday, this era, you started to be able to see blue if you looked at a satellite picture of the Earth from space. The top end of the Earth in summer suddenly started to look blue instead of white. So we were changing the appearance of the planet. And so there in 2007 we had then this a huge sea, sort of, it's as half the, which is half the Arctic Ocean, became ice-free. And so that was when sort of people first started to appreciate that the sea ice is disappearing. But I guess I'd been warning them for about a decade or two from measurements that were done from submarines that the ice was getting thinner, so and they should expect it to start vanishing. But it came as a surprise to everybody when it actually happened. Okay, then 2012 it retreated even more, and the yellow is the 2007 summer ice edge, and then the white is 2012. So it lay even further back. Again, in the Beaufort Sea, there was another big retreat, but there was also a retreat to the north of Russia. So 2012 remains the record, just about. Since then, it's sort of hung about that limit, but it's got less in all the other seasons of year. So the volume of ice, the area of ice, is continuing to decrease all the time, but that little September minimum, it's still holding out, and it hasn't yet gone away, but it probably will pretty soon. So that's okay. That's what the ice has been doing, and we can relate that back to global change, but the question here is, why is the Arctic ice retreating so fast compared to other aspects of our climate in the world? We don't see other things changing as fast as the Arctic is changing. And the reason is that the Arctic is warming up about 3 times as fast as any other part of the world. And we can see that because this famous curve, which climate change deniers put an enormous amount of effort into discrediting this curve. And it's called the Mann-Bradley curve of the world's temperature over the last 1,000 years. And it's called a hockey stick curve because, as you can see from the bottom, the world in the year 1000, when there was the Viking colonies in Greenland, the world was slightly warmer than it later became, and then the average temperatures over the Earth gradually got colder until, again, 1850, and then suddenly they shot up again, and that was the Industrial Revolution. So this hockey stick curve, which looks like a hockey stick, it's clear that it's the Industrial Revolution and the release of carbon dioxide from burning fossil fuels that produced that huge jump, and before that, over 1,000 years, you just had minor fluctuations due to sort of random changes. And this is the best record we've got. They used every possible measurement. There were, thermometers going back about a couple of 100 years, and before that, measurements of tree ring growth, measurements from corals, ice core measurements, the top parts of these ice cores. And so this is a very reliable curve, and therefore it had to be discredited because it showed it very clearly that it was the Industrial Revolution that produced the big warming of the planet. And so, in fact, the climate change deniers appointed some of their own cronies to re-examine the data, hoping that this would prove, this was funded by the Koch brothers, that this would prove that this was yet another hoax, possibly Chinese, but unfortunately for that they found that it was actually correct, and this data still stands, and even the people who did that study on behalf of the climate change deniers still said, no, this is true. And so there it is, this is what's happened. If we blow up the last 150 years, which is the top curve, we see that the Earth was warming up quite fast, but it did pause or go back a little bit between 1940 and 1970, and then it took off again. So that's something that needs to be explained. But we can see that the warming from the middle of the 19th century until today was about 0.8 of a degree. That's the average temperature of the Earth. So the global warming, man-induced global warming from the Industrial Revolution has been about 0.8 of a degree so far. But when you look at, that's the world as a whole, but when you look at the Arctic, which hopefully we can look at in a minute, but there we are. Okay, when we look at the Arctic, and this is just since 1900, and compare it with that previous curve, I showed that the top curve showed that the planet really warmed up rapidly, stopped warming, and then took off again. Now, if we just look at the data from north of 60 degrees, this is data from weather stations between 60 degrees and the North Pole, then we see the same pattern, that the world warmed up rapidly. It went back a little bit from 1940 to 1970, and then it took off again. So we see the same shape, the same response in shape, but a different magnitude. Instead of warming by 0.8 of a degree, it's warmed by about 3 degrees. If you look at from -2 to plus 1 and a bit. So it's the same shape of change, but the magnitude of the warming in the high northern latitudes has been about 3 to 4 times as great as the warming of the planet as a whole. So the Arctic is taking off and warming itself much faster than any other part of the world, and that's the reason why the ice is retreating so fast. Well, okay. This is actually the amount of warming we've had in this case since 1950 at different latitudes, and we can see that if the average, the Arctic is warming much faster than the global average, several times as fast, and of course the rest of the planet is warming at less than global average to offset that. So we really have a strange thing going on in the Arctic called Arctic amplification, and we're getting a more rapid warming, but which is not fully understood what's causing that. But if you then extrapolate into the future, and you have these are these 3 scenarios I mentioned yesterday when the Intergovernmental Panel on Climate Change was trying to predict what would happen to the planet. You could have, well, they now use a number of different scenarios, but in the early days they used 3, that we either have business as usual, where we let the world go on with its business and emissions continue to increase, or we can really seriously do something and reduce emissions, or we can really deliberately stimulate more emissions, do a Trump, and let's burn as much coal as we can get hold of. And so the top one, the bottom one here is the Trump approach. The middle one is business as usual, and the top one is sort of virtue. So business as usual is the most likely, and we can see that the fact that the Arctic is warming faster than the rest of the world means that by the year 2000, the Arctic will be this is about 7 or 8 degrees warmer than it is now, while the rest of the world will be about 4 degrees warmer, which itself is disastrous. I mean, if the whole world warms by 4 degrees, then that'll be a sort of catastrophe. But the Arctic will be warm by twice as much, and that'll mean a vast amount of ice melt, causing global sea level rise. So that's what the predictions are, based on the fact that we have this Arctic amplification going on. We're going to get a very, very warm Arctic in the next few decades. Well, and a very, very warm planet, but but the Arctic will be warmer still. Then what does that mean for the ice as well? It means that the ice that I showed at the beginning, the big solid ice flows, aren't there anymore, because nearly all the ice now in the Arctic melts in the summer and then forms again in the winter. So it's called first-year ice, which is like the ice you get in the Antarctic. Whereas in the past, it would sit there or drift around, but get thicker every winter. So when you went out on it, you were really dealing with a very formidable landscape. This is what MultiYear Ice used to look like north of Alaska, and this is in summer, in fact. So this water you see here is meltwater, which has melted off the top, but is still sitting there and will freeze again in the autumn. So it's like the Grand Canyon bit, and it's very formidable ice. It's lost most of its salt. It's really heavy ice. You can't break through that, where you could just about break through it with a Russian nuclear icebreaker, but not with anything else. And that's the way the Arctic looked when I was young, and I used to work up there. This was really exciting to go and work in this kind of landscape. It was that MultiYear Ice was very formidable, exciting stuff to work on and drill holes in and study. But now there's scarcely any MultiYear Ice left in the Arctic, and this is what well, the background picture here is what the Arctic now looks like in the winter. It's called first-year ice. It's very thin, and it's formed that year and melts again in the summer. So it's weak, it's thin, it doesn't have these big rugged ridges in it. It looks really a bit pathetic, and it is quite dangerous to work on. And this is the amount of MultiYear ice. It was only in the last 15 years or so that MultiYear ice disappeared. So before the year 2000, you had that kind of dramatic landscape that I showed first of all, and then the amount of MultiYear just went right down during the 2000s. And there's a satellite which can detect the difference between MultiYear ice and first-year ice. So the red is MultiYear, and MultiYear ice used to dominate the Arctic, and that's the way things still were in 2004. And then each year since then, the amount of MultiYear ice has decreased. And I've got a more recent one here. I'm not sure which time. Oh, here we are. This was 2012, and the MultiYear ice is red, and there's just a little fringe of it across the north of Greenland. That's all the MultiYear ice that's left in the Arctic. Well, the blue is a little bit of elsewhere, but mostly it's gone. And so we're now got this thin first-year ice cover like you have in the Antarctic. Okay. So that was the extent, and it was of course, you can't avoid detecting that the ice is decreasing in area. But what the scientists and the modelers didn't realise was it's also getting thinner. You would expect maybe that if it's decreasing in area, it must be getting thinner as well, but they didn't sort of connect that. And so the measurements of how thick the ice is more difficult than the area. The area you see from a satellite, but to measure the thickness, you have to go underneath and then use an echo sounder looking upwards to tell you where the bottom of the ice is. So that work was done from submarines. So for the last few decades, we've needed scientific use of nuclear submarines to tell us how thick the ice is in the Arctic Ocean. There hasn't been a satellite that can tell you ice thickness, only area. And there still isn't. In fact, there is a satellite, but it's not generally regarded as giving very reliable results. So we still need to go underneath the ice and look up to measure the thickness. So the two countries that have done that work been United States and Britain, and Russia's done it, but it's never published any results. So I got involved with the British end of this right from the start of the first British submarine in the Arctic. So I've been going up there with Royal Navy submarines measuring ice thickness for 40 years now, and it's been a very, very fruitful thing to be able to do, and a great privilege to be able to sail on a submarine. At least it was until we had a fatal accident, but it's otherwise it's very useful. So this was the first trip I was on, and this shows the submarine, the Sovereign, surfaced at the North Pole, and so this is the, whoops. But the reason I wanted to show it is just that's how you did things then, and you still do them the same way. And but the first surprise when you go under the ice and look up is just how rugged the bottom of the ice is. You see these landscapes of ice and you sort of think, well, it's fairly rough, but you can see it's basically a flattish landscape. But underneath you have this network of pressure ridges which are very, very deep. This well, quite deep. This one is 40 meters deep, and we've measured pressure ridges up to 50 meters deep, and they're caused by the ice opening up because of the wind causing ice flows to move apart, and then new ice grows in the gaps. Then the wind closes the ice up and pushes it down under the surface of the sea, and it piles up a ridge. It's like a kind of slag heap, but a linear slag heap of blocks of broken up ice, which freeze together and give you a really formidable obstacle. So this is, oops, here's a series of pressure ridges showing you how deep they are, and then the flat bits are they're not very flat, but they're the undeformed multi-year ice, and then the thinner stuff is first-year ice and leads that are refrozen. So we can see the whole under ice landscape here of undeformed ice that's fairly flat, the ridged ice, which is really formidable ridges, and about half the ice is in the form of ridges. So immediately you have to start profiling this. You've got to measure the distribution of thickness, the numbers of ridges, how deep they are. You immediately have a job to measure everything here and then try to understand and model why the ice produces this kind of appearance. So that was what I was busy doing for many years. But eventually I noticed that we were sailing over the same terrain in successive voyages. And in fact, I got the submarine to follow the same tracks as it had followed on an earlier voyage. And so for the first time we were able to see how the Arctic ice had changed over an interval. And in this case, the interval was 11 years. And so we had one data set from 1976 and one from 1987. And this was 1976 on the left-hand side. These are contours of ice thickness. And we can see that it got pretty thick north of Greenland, 5, 6, 7 meters. And the rest of the Arctic, this area of the Arctic, was about 4 meters thick. Then in 1987, we were surprised to find that where it used to be 4, 5, 6, 7 meters, it was down to about 4 meters, 4 to 5 meters. So that big change happened between there and there. And then, so I published that in Nature in 1990, and that was the first paper on ice thinning in the Arctic, and that showed a decrease of 15% in ice thickness between those over that 11-year period. But then when you keep on looking, you find in 2004, for instance, that's this top right-hand curve, that the area north of Greenland, instead of being 7 meters going down to 4 meters, is down to 2 meters, 2 to 3 meters. That's that much lower thickness. So the thinning has carried on happening, and there we are. That's an interlude to show you what life is like on a submarine if you're a civilian. If you're a civilian, you get to sleep in a torpedo tube rack. So this is my colleague from Cambridge, and showing our home, which is, they clip a bunk to a rack, the torpedo rack, where there isn't a torpedo, and you get to sleep there. Of course, when you wake up in the morning, as soon as you lift your head, you bang yourself against some metal thing, and so you always end up with a mass of bruises. And when they have exercises loading the torpedoes and unloading them, you have to go and hide in case, so you don't get loaded yourself. And then you've got these missiles as well. You're trying to sort of save the world by measuring the ice thickness changes, but the captain is trying to sort of practice making war. So it's a kind of slightly bizarre world where, as a civilian on a submarine, and then this was the most recent voyage that I did, which was 10 years ago now. The reason was we had an accident on board, and there were 2 sailors killed. We were doing, for the first time, I was putting a multi-beam sonar on the bow of the submarine, which actually measures gives you a kind of 3D map of the underside of the ice. Instead of just a profile, you have a nice map and you can see the ridges. So it's really very, very nice, improved way of measuring the bottom of the ice. And so it was really the best voyage I'd ever done on a submarine, but unfortunately it was the last one because the British Navy stopped sending submarines to the Arctic at that point. There was an explosion on board from a faulty oxygen generator, and 2 sailors were killed. We were under the ice, the submarine caught fire. It was pretty gruesome. I was expecting to die any minute, but we managed to surface and get everybody out. And so it was very nasty. It was again a human failure, as usual, that they reloaded faulty oxygen generators, which they'd sent back, and the parts department in the naval base had said they must use them anyway, even if they were faulty, because they wanted to save money. So that led to 2 people's deaths. Anyway, this is just another scene. If you want to take some pictures along and hang them on the wall, you can't, because there isn't any wall to hang pictures on. This is every square inch on the submarines has got some instrument or pipe or something. And the other useful thing that you can do as far as properties of ice are concerned is that not only do they take the submarine where you want to go, but they'll also put you ashore, or put you on the ice, and then you can measure the forces involved when the submarine breaks through the ice. So here they put us on an ice floe, went underneath in some fairly thin ice in a lead, and then surfaced, so we were able to measure the forces that it exerted on the ice. So here it's just breaking surface, and then then here it is emerging at the bow and the fin, and then there it is up. And because then they took us back on board again, so they had to do it in the right place, otherwise we'd be marooned in the middle of the Arctic forever. And this is sort of data that it collected, and it's very high quality, and it shows you, in this case, a pressure ridge. Instead of just seeing that thing like a triangle, you can see the whole shape of it, and how long it is, how it interacts with the next pressure ridge, and so on. So it's a marvelous. We're still working out what the data means. So there we were doing that, and that's what what's been providing the information on the thinning of the ice. And a typical submarine voyage would take you right across the Arctic, so you sample the ice around Greenland and in the north near the pole and in the Beaufort Sea. So in fact, in that case, the place where we had the accident was just north of Prudhoe Bay. Okay, well, the first thing you find when you look at all these ridges is that the yellow ones here are the MultiYear Ice, and the purple is the first-year ice. So the MultiYear Ice has these big, deep pressure ridges, but the first-year ice, this thin stuff we now have, has got a lot fewer ridges. And so we've carried on, because we had to give up using submarines, and we've carried on doing this with autonomous vehicles called AUVs, which do the same job, but they don't have a person on board. You program them to sail under the ice, do a crisscross pattern, and then come back up. And there's a lot of technical problems involved in getting it to come back where it started from, and you don't get such a long distance track either. So it's a hell of a lot of effort for much less data than sitting in comfort in your submarine, but at least you're not there under the ice. And this shows us some of the scenes of doing this. That was okay. This is you cut a hole in the floor of your tent, put the vehicle through, and we were measuring this pressure ridge on the right there. And the red and black tent in the background is where we launched the vehicle from. Then this is showing in another part of the Arctic building our own camp. So we went out from a Canadian base out onto the ice with all this stuff, built our own camp, and built another tent to live in. This is the hole in the floor. And so there's all this effort required to get about a tenth as much data as a submarine used to get. So I'm not a fan of AUVs. I'd rather be back on submarines, but they have to make them safer first. And this is that pressure ridge, and we can see the detail that using an unmanned vehicle, you can get closer to the ice because you don't have to worry about hitting it. And so here's the very high quality picture of the bottom of the ice. And in fact, you can see how good the quality is because the red circle shows these very tiny individual blocks in the ridge. And then we had a diver go down to that spot and he could see those blocks. That's on the right-hand side. So you can see that it was really showing what was there. Then this is another part of the Arctic also with an AUV with a multi-year flow, and that's a multi-year ridge, and you can see more formidable sort of structure there, bigger blocks that would be much harder to break through. But you take all that data from those subs and the American subs and add it into the extent data, and we get a volume. The extent, we know the area is... we know the area, but now we know the thickness as well, which is also decreasing. You multiply the two together, you get the volume, and it's really going down. And so in 2011, the volume of the ice in summer was only a quarter of what it was in 1979. So in summer Arctic ice, you look at the Arctic Ocean in summer, there's only a quarter as much ice as there was only 30 years ago. So that's a massive change in a part of the planet. And the way that's been expressed recently was a thing called the Arctic death spiral, which this was at Boulder in University of Boulder University, the University of Colorado. They came up with, what they did was to have a clock pitch curve where the distance from the centre is the volume of ice for a given month of the year, and you start off in 1979, you come round to the present day. And the black line is September, and the green is winter months. So September is the nearest to the centre, which means the least ice. And if there was no change going on in the Arctic, then this would just be a series of concentric circles. But because the ice is disappearing at all seasons of the year, each of these curves is coming in towards the centre, so it's forming a spiral. And the first one to reach the centre will be September, and then there will be August and October will follow quite quickly afterwards. Then the rest of the months will last longer. We don't know how long, but eventually all the ice will disappear. But that's the death spiral, which is, I think, a very good graphic way of showing the seriousness of what's going on. You can extract September alone, just look at that, and we can see that's heading down exponentially towards zero. And this shows it reaching zero in 2017, which it didn't manage to do, but there's wiggles on that, so this is 2016. This is from my book, and this is just looking at the ice area in summer, or coming down towards summer and then back up towards autumn. And the bottom line, the red line is 2012, which was the record. But then 2016, which is the black line, you can see through most of the year that was a record low for the time of year. But when we went on to summer, it just nicked the bottom of the curve here and didn't quite reach the 2012 record. But for most of the year, the 2016 was the lowest area of any time. Well, we better go back to what's causing all this. The amount of forcing that's causing this warming is, we can divide it up into the sources of warming, and this is what IPCC has done, and they're called radiative forcing components. What's happening is, if say you put carbon dioxide into the atmosphere, it is actually like a greenhouse. It allows all the shortwave radiation from the sun to come down straight in, reach the planet, but the radiation from the sun causes the Earth to warm up, and the Earth then emits its own radiation, long-wave radiation, due to its temperature. Everything in the universe emits radiation at some level which depends on its temperature. So the Earth is emitting long-wave radiation with infrared, and the CO2 absorbs the outgoing infrared, so it's stopping the radiation from the Earth from getting out, but letting the shortwave radiation from the sun come in. So we're getting an imbalance, which you can express in terms of a difference in radiation between what's coming in and what's going out. And CO2 is the biggest single source of that radiation imbalance at the moment. But methane is kind of catching up on it. Okay, back again. So CO2 is the biggest. Methane is following about a quarter of the CO2 levels. There's some halocarbons still affecting the world, even though we've stopped using them. And then there's some, to offset it, there's some effects of clouds and aerosols, that's air pollution, which actually act against global warming. But the net result is that the total is about the same as the carbon dioxide alone. All the others have a minor effects. And that's increasing all the time because the CO2 level in the atmosphere is increasing. And as it increases, it takes out more of the outgoing long-wave radiation. And so that makes that balance worse. And so the Earth has to warm up to restore the balance. So you always get a warming. If you add CO2 to the atmosphere, it'll always absorb more outgoing long-wave radiation. That will always mean that the Earth has to warm up to match the outgoing and the incoming radiation. So it's a kind of high school physics that add CO2 to the atmosphere, you get warming. You know, to deny that is kind of idiotic. And all the climate change deniers, including all the politicians, are absolute total idiots. I mean, they failed to... It's like saying that the Earth is flat because you can't see the bend. It's like saying that gravity doesn't exist. It's that kind of level of mentality that is really low. And so I can't believe that the people who say that CO2 doesn't have any effect on global temperatures, that they can believe that. Either they don't believe it, but they say it because they're in the pay of the fossil fuel industry, or if they believe it, then they're total morons. I mean, we're ruled by complete morons, up to and including the president. So that's my view of having studied, you know, if you go through the physics of how CO2 causes global warming, there's no way that you can not see very, very simply that it does, and that the more you add, the more warming you get. It can't cause a cooling, or it can't do nothing. It causes a warming. So anyway, that's... but then, because therefore the more CO2 we have in the atmosphere, the worse our warming. And it's the level that matters. It's not the emissions. And that's the other frightening thing, that we get... we can say we're reducing our carbon emissions and feel all good about it. But as long as we've got any emissions, more or less, we're increasing the level in the atmosphere because the carbon dioxide stays around for hundreds of years in the Earth's climate system. It doesn't go away. Like methane goes away, it oxidizes in a few years, but carbon dioxide doesn't. So it's not enough for us to reduce carbon emissions. We've got to actually stop carbon emissions, or get rid of some of the carbon that's already in the atmosphere. So that's something I'll talk about this afternoon. But as it stands, these are the villains, and who are the villains? Well, actually, we're all villains, but these are the emissions by different countries. It's about 5 years out of date, but we can see that the US has gone down slightly. Europe, that's the EUR, has gone down slightly, and this is the rest of Europe, has gone down slightly. So we can all feel good. Wow, aren't we good? We've reduced our carbon emissions. But the only reason they've gone down is because we transferred all our industry to China. So all the stuff that we used to make with efficient factories is now made with inefficient factories in China. So China's emissions have gone right up, and so have India's. So the net emissions of carbon dioxide continue to increase, even though Western Europe and the USA feels good about reducing their emissions. They've only just transferred their emissions to China and India. So the net is going up, and and we notice that the curve mentions cement, especially because cement is the worst stuff in the world as far as climate's concerned. We should never use cement for anything, because when you produce cement, you need a lot of energy to produce it. But at the same time, the chemical reaction that occurs when you turn lime into cement produces carbon dioxide. So it's, you're getting much more carbon dioxide produced per unit of cement than anything else. You could build houses out of glass or steel or bricks or wood, best of all, and it uses much less energy than cement. So concrete houses are a disaster, concrete buildings are a disaster. Unfortunately, China is the worst offender here because they've got a state-owned cement industry which only, you know, the people who run it only avoid being put into jail or beheaded or whatever by producing ever more cement. So all the new ghastly Chinese cities have all got 15-story concrete apartment blocks producing vast amounts of CO2 in their production. So it's a pretty sad story, and it hasn't changed. And so we are doing nasty things, and we're not even reducing our emissions; they're still increasing exponentially. So that's what we're doing, and we've reduced the area of ice in the world. This is the September again. I'm going back to the sea ice again, and the red shows what's actually happened, and the black shows the predictions of various climate models. So we can see that climate models are very inadequate and very complacent. So when scientists were, I mean, last night people were saying some things about scientists not being totally good, well, not totally honest, but I think the climate modelers, they're honest, but they don't pay any attention to data. So they've predicted this curve as being the volume of ice in summer, and you can see that there's still plenty of ice around in 2100 according to their models. But unfortunately, they weren't going to the Arctic themselves. They were sitting in a desk, at a desk somewhere. So unknown to them, the actual reality was doing this. So we're down, in 2012, we were down to a volume of ice in summer, which matches what the modelers said we get to by 2100. So there's something really seriously wrong with climate models, and that needs fixing. Now that the climate people have acknowledged that they're up the creek. So I'm coming to the end of my this morning's talk. So I was going to sort of divide up and start talking about the impacts a little bit, and then carry on this afternoon with impacts. So what I've said so far is what the Arctic's done, but that sea ice retreat is having global impacts which are greater, much greater in fact, than the direct impact of the ice retreat itself. So I'll deal with just two of them, well, three of them, now, and then go on this afternoon to talk about some more. So if I run out of time, I'll just add it on to this afternoon's talk. So the first thing is albedo feedback, and albedo feedback is the direct effect that as sea ice retreats in the Arctic, it accelerates global warming because you're taking away white stuff, which is the ice, and replacing it with dark stuff, which is open water. So when we, I'm sure okay, the left-hand picture shows a typical summer scene in the Arctic where the ice is melting, and you can see that the open water is dark, the ice is bright, and the ice has an albedo of about 80%, so about 80% of the radiation that falls on it is reflected straight back up, but only less than 10% of the radiation that falls on open water is. So the contrast between ice and no ice is an albedo of 80% versus 10%. So as the ice retreats, suddenly, and the world gets darker, and that means the world absorbs more radiation, and it accelerates global warming. So it's a positive feedback. Positive not meaning good, it means making things worse. So the positive feedback of albedo change accelerates global warming. So that's the first direct effect of sea ice retreat. And this was calculated by in a paper in 2014 by Pistone, And they just looked at, here's the Arctic in summer. The black stuff on the left used to be ice and isn't anymore. So you turn that area from white to black. What does it do? It adds a lot to the radiative forcing, 6.4 watts per square meter. It reduces the average albedo of the planet, and it's equivalent to having an effect on the whole planet equal to a quarter of the effect of the direct effect of adding greenhouse gases. So you're adding greenhouse gases, causing the ice to retreat, and that retreat is like adding another 25% to the warming. But in fact, that's inadequate, as I'll explain this afternoon, because it doesn't take account of the fact that the snow retreats as well. That adds another quarter. So it's in effect, we're adding a half to the global warming effect of adding CO2 to the atmosphere. We're making the effect half as bad again, because that causes the ice to retreat and the snow to retreat. So it's a sort of getting on towards a runaway. It would like to be a runaway global warming like Mars, but it's not quite reached that. But it's kind of frightening that the things we're doing cause an acceleration of the warming. We're causing a feedback, planetary global feedback, just from an effect in the Arctic. So that's why I'm feeling very concerned about the Arctic, because it's not just a local thing. It's not just glaciologists saying, oh dear, my favourite ice has gone. It's that ice is affecting the whole planet. Okay, here we are. Well, first, what are the effects? Well, first of all, that if we look at the temperatures in November of 2012, for instance, and we look at the top of the planet, we see big red splodge, which is a very large warming, a large warm anomaly that shouldn't be there because the ice hasn't reformed yet, whereas it normally does. So that's a big warming, which has another big albedo effect. So this is sort of typical of how the Earth is responding to this. Here we are. And then the other thing, the second thing which I'll end on, is sea level rise, and that's that's most frightening because it's inexorable, because it's going on, it's accelerating. We're standing on this exponential curve where we look behind us and the sea level hasn't changed much. We look ahead of us and it's going up vertically. And the reason why this has been accelerated by the loss of sea ice is it doesn't directly affect sea level. Like when you melt sea ice, it doesn't change sea level because it's like melting an ice cube in a drink. It's already afloat, so it melts, doesn't do anything. But the thing that it does do is the retreat of the ice causes the atmosphere to be warmer over the Arctic. That warm air comes in over Greenland and warms the atmosphere over the Greenland ice sheet. So the Greenland ice sheet starts to melt, and that really does put water into the ocean and cause sea level rise. So here we see, well, that previous picture showed warm air coming in over Greenland in recent years. And then in 2012, for instance, we see that early in the summer, it was typical of a previous typical summers in Greenland. You get a little bit of melting around the edges of the Greenland ice sheet, but not in the centre. But in 2012, the right-hand picture shows almost the whole of Greenland was melting in the summer because of all the warm air that came in because there was so much open water around in the Arctic. So the open water in the Arctic leads you to warm air over Greenland. The warm air over Greenland causes the Greenland ice sheet to melt, and the melting of the Greenland ice sheet dumps fresh water into the ocean, and that accelerates global sea level rise. So we've got immediately a feedback between sea ice retreat and global sea level, which is a very, very serious one. And in fact, we now know how much mass is coming off the Greenland ice sheet because we've got a a wonderful satellite called Grace, which is a pair of gravity measuring satellites that move together a few meters apart over Greenland. And as they move over the Greenland ice sheet, or over the edge of the ice sheet, or over anything on the planet, the distance between the two satellites changes because one satellite encounters a different gravity field before the next one, and they move together or they move apart. You can calculate how much extra mass there is underneath you. So when you fly over a big ice sheet like Greenland, it will calculate how much ice there is, which is very helpful. You used to have to sort of stick stakes in the glaciers and things, but now you just measure it with the satellite. But that shows that this decline of the mass of Greenland is accelerating. Everything's going exponentially, so that it's not just linear decline, it's an exponential decline. It's losing mass faster and faster every year. And all of that mass that's lost goes into the ocean, and that all causes sea level rise. So when we look at sea levels in the world, we see a steady increasing predictions of how much we're going to get. So up to the year 2000, we had the blue line, which was just a small amount of rise. Then, as soon as these effects on Greenland started, we had an acceleration. But the Intergovernmental Panel on Climate Change, which tends towards complacency, only had a linear rise of a few tens of centimetres, 20 to 40 centimetres, back in 2007. Then they were forced to acknowledge that Greenland is melting and that this rise is actually exponential. So their new estimates now take us beyond a metre. And the more observations that scientists do on Greenland and Antarctica, the more sources of rapid melt they see, and the more, therefore, the more water is dumped in the ocean, and the more sea level rises. So the sea level rise predictions are going up quite rapidly, and that of course has terrible implications for cities, coastal cities, and also for coastal areas in poor countries like Bangladesh, for instance. This is not a good picture, but it's one I drew quickly. It's that the bad effects of sea level rise are worse than you think, because when you think sea level rise of a metre, for instance, if we're in a Western country in Europe or Holland or something, you just raise the heights of all the sea defences by a metre and everything stays the same. But if you don't raise the heights of the sea defences, then that extra metre is going to really do you a lot of harm. And so a lot of cities don't do that because they can't be bothered, they haven't got the money, or they don't want people to know that all their coastal real estate is going to disappear, and this will upset the economy. So we find that the effect is far worse than you expect because of the properties of the bell curve, the normal distribution. If you look at this curve, for instance, imagine there's a spot on the sea surface there, and the black line is the distribution of heights of the water at that sea surface point in time. Depends on the state of the tide, winds, currents. It changes with time. And so you have that bell curve is the height of the sea surface there. Now, supposing some distance above the average, you cause a flood disaster, and that's that black bit. So the probability of your flood is the area of that black curve at the top end. Now, supposing you now increase sea level, the whole curve moves up, but the area that's above this critical point becomes much bigger. So you think you're having a small increase in average, but the increase in the probability of a disaster goes up much faster. And that means places that can't raise their sea defences, like Bangladesh, around the whole coastline has got millions of people living on it, 20 million people live less than 6 feet above sea level, those 20 million people get occasional floods from the storm surges in the Bay of Bengal. But if the sea level, global sea level goes up, those floods will become much more frequent. And those floods kill a few hundred people, perhaps, in Europe or America. But in the Bay of Bengal, they kill hundreds of thousands of people. And those disasters will become much more frequent because of global sea level rise and poverty, which stops people who live in crowded coastal areas from raising the heights of their defences or moving inland even. So sea level rise is a disaster primarily for poor countries, but it's a economic disaster for rich countries. I mean, it will mean Miami will have to be abandoned, and already New Orleans ought to be abandoned. So that sea level curve is inexorable because it doesn't, even if we reduce our carbon emissions, it will take a long time before the rise of sea level slows down. It's like because it's so many sources of it, so much melting of the two ice sheets causing it. So there we are. That's sea level rise. That's just one of the bad, perhaps the worst effect apart from the direct warming. So I'll carry on this afternoon with hopefully continued gloom, but with some hope of what we can do to save ourselves, which I think we can do something.